are going to do today is have a talk about ionisation energies in the hydrogen atom, and that's kind of using this model, Bohr's model of the atom, and understanding it in terms of like what we know about ionising. What do we mean when we say ionising something?
What is it? Stripping electrons off stuff.
Stripping electrons away from it. So what energy level are we targeting if we're trying to ionise the hydrogen atom? 3.
Infinity.
What about infinity? Good. We want to ionise the hydrogen atom. We have to take that electron up to energy level number infinity, right? So that's kind of what we mean by the ionisation energy, is the energy required to take the electron up to energy level infinity, an infinitely large distance from the nucleus. Infinitely large energy gap. Except it's not infinitely large energy, we're going to measure it right now. And so the weird thing about these energy levels in the hydrogen atom is that they get progressively closer and closer and closer together. So the jump from 1 to 2 is the biggest, 2 to 3 is smaller than that, 3 to 4 is smaller than that, and then it's not far to infinity after that. And so what we're interested in is calculating the energy level to infinity. And so remembering that E is HF for any photon, and that F is V upon lambda, which is just C upon lambda, and that lambda, well, 1 over lambda is R 1 over S squared minus 1 over L squared. And so what we can do is combine these equations together. We can rewrite frequency using this equation. Instead of writing over lambda, we can have R 1 over S squared minus 1 over L squared. So, and then we can plug that into energy and say that the energy difference between any two energy levels. And so what we're going to do is we're going to plug in that we're trying to go from the higher energy level, the infinite one, so L is infinity, and in fact 1 over infinity is just 0. And so this equation is going to lose that minus 1 over L squared part. And we're going to rename S as N to match the numbering code of our energy levels. So we end up with an equation that looks like En equals HCr over N squared. See, we're going to put a minus sign out the front. And the reason for the minus sign is because when the electron is ionised, that's when it's completely free from the influence of the nucleus, of the atom. And that means that as it goes down to a lower energy level, it's getting more and more tightly bound to the atom. And so it's minus because that's the work we have to do on the electron to free it. Once it gets up to energy level infinity, it's got 0 binding energy, it's not bound to the atom anymore. And so that's what our equation looks like to tell us the ionisation energy of any of the energy levels of the hydrogen atom. And the minus, that's the critical thing. So this is a really important concept for us in this nuclear physics topic going forward from here, this concept of binding energy, and that binding energy is the amount of work we have to do to separate things. And so in this case, it's really easy to visualise that as we move the electron up the energy levels, we have to do work on it. We know we have to do work on it because when it falls down, it emits a photon, so it's releasing energy. So it makes sense that we have to do work on it to push it up the energy levels, and that once it's completely free, it's got zero binding energy, nothing is binding it. So it kind of makes sense that the binding energy is negative. It represents the amount of work that we have to do in order to get that electron up to a point where it's unbound, where it's a free electron.